It's me again and you again, and we're looking once again at equilibrium systems and how a system looks when you apply a stress to it and you have a concentration curve. You probably remember when we did a little while back systems that had three curves. We did one with ammonia where the nitrogen was getting used and the hydrogen was getting used and ammonia was getting made, and the traces looked like that. You can use that kind of graph to keep track of what happens to a system as you mess with it by applying various stresses, and they have distinctive looks that we want you to get used to. So here we have a system with carbon monoxide reacting with oxygen, turning into carbon dioxide and releasing some heat. And they've tracked the concentrations of all of these things, and basically they want you to try and tell the story of what each of these changes was. So how do we do this? The system starts out at equilibrium, everything's flat, nothing's happening, and then at point A we come along and change something, and what do we see here? The concentration of carbon monoxide goes up, and oxygen goes up, and carbon dioxide goes up, all at the same time. There's a couple of ways this could happen. One of them is we just opened the system and injected all three gases into it all at once so that the concentrations all jumped simultaneously. That is possible. Another explanation, though, if you think about it, concentration is the number of moles of something divided by the volume it's in. So we could have increased the number of moles, or the other way you could get a higher concentration is drop the volume. If we take this system and suddenly crush it, the volume drops. That makes all the concentration spike all at once. And that would also explain what we're seeing here. So this could be reactants and products added simultaneously or volume drop. I'm going to go with volume drop. That seems more likely to me, but the injection thing is not crazy either. Okay, now after that, notice the system has been knocked out of equilibrium and it recovers a little bit. It uses up some carbon monoxide, that drops. It uses up some oxygen, that drops. So both of these go down, and obviously that would mean the carbon dioxide should go up, and sure enough, it does. It rises a little bit. Then the system finally settles down, and just before B, the system is going, ah, good, we recovered from that. We are stable again. Then at B, we mess with it again, and what do? Nothing happens immediately to the CO. We don't see a big up or down here, or to the oxygen, but look at this. We do get a sudden, abrupt drop in the carbon dioxide. If you have a single line like this, that should mean that somehow we just extracted some carbon dioxide from the system. You'd have a purge valve or something where you could force out this gas. So some of the carbon dioxide disappeared really quickly, and after that, the system is going to react. What would the system do if you take away carbon dioxide? It should make more carbon dioxide, use up some oxygen, and use up some carbon monoxide. And sure enough, that's what happens. CO drops, oxygen drops, the system makes a little more CO2 trying to replace what was lost. And it does that and eventually finds an equilibrium, and just before C, these lines are flat, the system has recovered again. So we're basically annoying this system in a bunch of different ways, and it keeps recovering from them, and each time it calms down, we hit it with something new. What's next? At C, nothing jumps up or down abruptly, but after we did something at C, the system starts to shift. So if we didn't add carbon monoxide, because there's no sudden spike here, and we didn't add any oxygen because there's no spike there, and we didn't add any carbon dioxide because there's no spike there, what else could we have done? Well, according to the reaction, we could have added heat, right? What would happen if we put this system on a burner and started pumping heat into it? Let's see if that explains what's going on. If we added heat and that was our stress, then the system would push back by consuming heat, consuming carbon dioxide, making oxygen and making carbon monoxide. And here we see, here's carbon monoxide going up, like it says. Here's oxygen going up, like it says. And here's carbon dioxide dropping. So the stress at C is probably, we put in some heat. And then the system settles down. And when we get to D, it doesn't seem like anything happens at D. So if they're saying we did something to the system at point D, your choices would be, well, can you think of anything you could do to a system that does nothing at all to its equilibrium? If you had to pick something, how about a catalyst? We know they love to ask about that. If you drop a catalyst into the system and it's already at equilibrium, then it can't get there faster. It's there already. So the catalyst just sits there and there's no effect. And these lines just remain flat. That would probably be my pick for D. If it couldn't be a catalyst, the other thing I thought of was if you had the same number of moles on either side of your reaction, you could change the volume and that would also do nothing. But we already know in this system it's got a big side with 3 moles and a smaller side with 2 moles. So that isn't it. That leaves catalyst as my best guess. Hope that's okay. And we will see you in the next Think.